I mean, I talked to Aaron and realized that he was really using somewhat different notation than what I'm using and what the book is using. So let me start by just clarifying the notation, because maybe having seen two different. So what I use the following notation, and I said it last time, but I want to repeat it because now I know that there was really a different notation introduced. So this is my notation for the formula phi gets value t in the structure M under the assignment S. So we have S goes from variables x1, x2, the set of variables, to the universe of the structure. S hat is the extension of this to all terms. So from all terms to U of M. So S tells me what is the interpretation of each variable, and S hat extends it to interpretation of all terms. So I will talk about S of X and S hat of T. But when we want to talk about the formula, I don't use this notation of S hat, but I use this notation. A structure M, so that's the first thing. The second thing is about relations in the structure. So if I have a language consists of relation symbols and function symbols and constant symbols, then a structure for this language consists of first a universe, which sometimes I'll write as a universe of M, but sometimes I'll just ignore not mention the M. And then for each of the symbols in the language, we need an interpretation in the structure. So here I will have R1 of M, F in M, A in M, and so forth. And what are they? So if R is a relation, the interpretation, so if R is a relation symbol, then say KRE relation symbol, then R of M, R in M, is a set of K tuples of the universe of M. So let me maybe demonstrate it with an example. So here is an example. So let's assume that my language has only one relation symbol, and this relation symbol is a two-place relation symbol. So I can have different structures for it. So I can have M1 could be the structure which is going to be the natural numbers, and this R is a set of tuples in the structure, so it could be the set of all A, N, M, such that M, N is less than M. So this tells me the interpretation of the relation R is the ordering relation. A pair satisfies the atomic formula. So now I'll have that M satisfies under S R of x, y, if and only if S of x is less than S of y. Okay, because I say how do I check if R of x, y is satisfied in the model under the substitution, under the assignment S? I put here what S assigns to x, I put here what S assigns to y, and I check if these, now I have here two elements of the structure. Do these two elements belong to the interpretation of the relation R? So this is the interpretation of R. This is R in my structure. So it's the set of all tuples for which I will say that the relation R holds. And I could have a different structure, say M2, in which, say, this is the natural numbers, and I have a different interpretation of the relation R. So it could be, say, the set of all pairs N, M, such that N divides M. So can you show me, say can you show me an assignment S under which M1 will satisfy under S the formula Rxy, and M2 will not satisfy under S the formula Rxy? Can you show me such an S? What? 2 and 3, right. If S of x equals 2, and S of y equals 3, then the first structure, the relation now is between 2 and 3. 2 and 3 belong to the set of pairs that are the interpretation of R in M1. But 2 and 3 do not belong to the set of pairs that are the interpretation of R in M2. Can you show me a sentence that holds in M1 and not in M2? By a sentence, I mean now I want a formula that does not have any free variables. So I don't depend on any assignment. So can you show me a sentence that holds in M1 and does not hold in M2? Now I want a sentence. I want a formula with quantifiers, with no free variables, that holds in one of them and not in the other. Yes?
Exists x, all of x and x?
Right. So, for example, if I look at the formula psi, which is there exists an x such that R xx. So if I want to check if it holds in M1, I have to check is there a natural number x such that x is strictly less than x, and it will fail in M1. So M1 does not satisfy phi. What will happen in M2? I ask, does there exist an x such that x divides x in the natural numbers, and it will be satisfied. So the truth value of a formula depends on the structure and the assignment. The truth value of a sentence depends on the structure. But depending on the structure could depend either on the universe of the structure or depend on the interpretation of the symbols. So I can take the same language and have different interpretations to the symbols and different universes. So let's just look at another language. Let me look at the language for some, or even this language. I can give it a completely different interpretation. I can say that here is M3. For the same language, M3, my universe is going to be P of n, which is the set of all subsets of the natural numbers. And my relation, the interpretation of R, will be the set of all A, B, such that A is a subset of B. So now I can check, for example, look at this sentence. Does it hold in M3? So I'm asking, does there exist an X such that X is a subset of X? So it will hold in M3. And can you show me a sentence that holds in M2 and does not hold in M3? So we can play all of those games, but we see that I can have all kinds of interpretations to the same sentence. The same formula assumes completely different meaning depending on what is my structure. Yes?
Exists X for all Y or XY?
There exists, so let's look at this. There exists an X, so let phi prime be there exists an X such that for all Y R X Y. Okay, so let's check it in both in the structures M2 and M3. What will it mean in M2? In M2 it will say M2 is this structure. It will say there exists an X such that X divides every other number. Is it true or false?
Yes.
It's true. Which number divides every other number? 1. What will it say in M3? There exists an X such that X is a subset of any other subset. I'll take the empty set. So it will be true in both. Okay? So it's not that trivial, but we can play those games. So it gives me a lot of room for writing exercises. Okay, so this leads me to the next topic I wanted to discuss with you. And somehow we want to know what can we express in this language. So I want to talk about the expressive power of first-order logic. So I will say that a set of structures is definable in a language L, in a first-order language L, if there exists a set of L sentences sigma such that, so let's give us the name, the set of structures, let's give it a name. Let's call it K, such that K is exactly the set of all structures such that M satisfies sigma. And by M satisfies sigma, I mean, namely, or meaning, for all phi in sigma, M satisfies phi. Because this is kind of abuse of notation to say M, we have this notation for M satisfies a formula. Here I say satisfy a set of formula, and this is just a way of saying it satisfies every single formula in the set. So this is very reminiscent of the notion of definability that we saw in propositional logic. But in propositional logic, what we defined is a set of truth assignments. And here I define a set of structures. So let us look at some examples. So let L So let us look at some examples. So let L be the empty language. So now I have no relation symbols, no function symbols, no constant symbols. I have nothing. I claim that I still can define all kind of interesting collections in this language. So I claim that, so let us look at one, the collection of all structures M such that U of M, the universe of M, has size 1 is definable in my empty language L. Can you give me a definition of this set of all structures that have exactly one element? So I want to write a sentence in the empty language. I'm not allowed to use any relation symbols or function symbols. That will hold in a structure if and only if the structure has exactly one element in the universe. Yes?
For all x, for all y, x equals y.
Right. So I'll have the sigma that will define it. Sigma 1 will be the set consisting of just one formula, and this one formula will say for all x, for all y, x equals y. So clearly this formula holds if I have in my universe only one element, because then the for all ranges only over this one element. So it will always give me the same element. Yes?
Do you have an empty universe?
No, by definition, a universe should be, right, if I had an empty universe, this will also hold. But by definition, we always assume that the universe is not empty. But let us, kind of follow up on your question. I claim that for every, no, why 3? 2. I claim that for every n, the collection of all structures with at least n elements in U of M is definable, as well as the collection and the set of all M such that U of M has at most n elements is definable. So I can both define the collection of all structures in which I have at least n elements, and I can define those that have at most. So how will I write a definition for all structures that have at least n elements? So let's call it sigma at least n. What should I put in my set of sentences? Yes?
There exists x1, there exists x2 up to xn, such that all pairwise not equal.
Right. So it will be a long formula. It will be there exists x1, there exists x2, there exists xn, such that, and now I will have x1 is not equal, I mean not x1 equals x2, and not x1 equals x3, and all the possible pairs. Or if I want to write it more concisely, I can say there exists x1 up to there exists xn, such that for all I not equal j, I, j at most n, not xi equals xj. So this is like a big conjunction. And. The main, the main thing I want to emphasize is this has to be finite, because every formula in our language is finite. Did they publish the marks of the midterm? No. They didn't upload it? Oh, I thought it was already uploaded. Oh, anyway, we marked it, and basically the class was doing very well. Nobody failed. Quite a few people got more than 100, which is not funny. It will carry over to your final. So, but one of the mistakes that I did see several times is people using infinite formulas. So you have to remember that every formula, both in propositional logic and in first-order logic, is always finite. So the end here is over all pairs x1, xi, xj, such that I and j is at most n. So this is a finite formula. Okay, so I have a way of saying, of defining the set of all structures that have at least n elements. How will I define the set of all structures with at most n elements? Okay, that's my old confusion. This is not implied. This is logically implies when I have formulas here and formulas here. But when I have here a structure and here formulas, it means those formulas are satisfied in the structure. This is just talks about the truth value being t. In this structure, every formula in sigma gets value t. So that's the confusion that we have to be careful about, because we are using the same symbol for two different things, and the interpretation only depends on what do we put there. So if I write M satisfies phi, this stands for satisfies, which means phi gets value true in M. And similarly, if I have here a set of formulas, every formula in the set gets true. If I write here sigma implies phi, what I mean here, this is logically implies. Which means for every structure that makes all of those true, this is also true. And the only way to distinguish whether I'm talking about interpretation satisfies or interpretation logically implies is the question of what do I have on the left-hand side. If on the left-hand side I have a structure, then it is satisfiability. If on the left-hand side I have formulas, then it's logical implication. So what I'm saying there is K is the set of all structures that satisfy all the formulas in sigma.
Okay.
So here we have implicitly a two-way inclusion. That is, every structure in K satisfies the formula in sigma, and every structure that satisfies the formula in sigma belongs to K. Okay?
And there's no, like, let's say if I come up with another structure, I guess I was confused that if I have a logical truth,
Right.
and wouldn't all my structure,
Right.
all my structures be finable?
Yeah, that's a good question. So that's a very good point. What happens if sigma consists of some logical truth? So here I have phi, where phi is a logical truth. In other words, phi holds in every structure. So what is the K that is defined by sigma? What is the set of structures that sigma defined? What? Right. So sigma defines the set of all structures. And this is very similar to the situation that we have seen in propositional logic. You remember? In propositional logic, we had this diagram. We said, here is all WAFs, all well-formed formulas. And here I have, instead of structures, I have here all truth assignments. And I could take here a set of phi of WAF sigma and look at the set of all assignments that satisfy sigma. Right? And we saw that if sigma is smaller, then the set of structures that will satisfy it will be bigger. Because if I have less requirements, more candidates will satisfy the requirements. And I saw that if I have here no requirements, like a tautology, it doesn't require anything, then I'll get here the set of all structures. And how do I get here the empty set of structures? What should I put in sigma so that the corresponding set of structures will be empty? In a contradiction. If no structure satisfies sigma, if it has a contradiction, then sigma will correspond to the empty set of structures. So the only difference is that in propositional logic we talked about all truth assignments, and now we talk about a much bigger universe of all possible structures. But the definition is the same definition. The concept is the same concept. Does it answer your question? So now, can you show me a set sigma that will define at most n? So here I had a sigma that defined the set of structures with at least n elements. Now I want a sigma that will define the set of structures with at most n elements. Yes?
Let's say for all x, there a y such that y always greater than or equal to x?
I don't have bigger or equal. My language is empty. Yes.
For all x1, for all x2, for all xn plus 1.
Right. For all x1, for all xn, for all xn plus 1. What will happen? O on I not equal j, xi equals xj. Right? If I try to pick n plus 1 many elements, inevitably at least 2 of them will be the same. Either x1 will equal x2, or x2 will equal x3, or x1 will equal x7, and so on. So if I try to pick n plus 1 elements, at least 2 of them, or over all pairs, will be equal. So if we call this formula, if I give this formula a name, let's call this formula phi n. So this formula, I'll call it phi n, and this formula, I'll call it psi n. So now how will I say that my structure consists of exactly n elements? Can you give me a sigma that will tell me the structure has exactly n elements? Yes?
Phi n and psi n.
Right. I'll say phi n and psi n. Because this one will say I have at least n elements, and this one will say I have at most n elements. So if I require both of them together, I will get the requirement that I should have exactly n elements. So now let me ask you a little slightly harder question. Can you give me a definition of the set of all infinite structures? Remember, we are only allowed finite formulas. So now I want sigma infinite that will define the set of all structures whose universe is infinite. Now I cannot write an infinite formula. But what can I do? Yeah, anybody? I'm sure you can do it. Just remember that we talk about, until now, we did not at all take advantage that I'm allowed to use a set of formulas. All my definitions so far were just one formula. But I'm allowed to use a set of formulas. So how will it save us when we try to say the set of all infinite structures? Yes?
You can have an infinite set with at least all natural numbers. So sigma has phi 1, phi 2, phi 3.
Right. Right. So sigma is going to have to be the set of all the at least requirements. So it was phi 1, phi 2, phi 3, phi n. So sigma will be infinite, or I can write it like this. It's the set of all phi I such that I is a member of n. So note that each phi I is finite. Each phi I is this formula that I have here, phi n. Each of them is finite, but I have an infinite collection of requirements. Each of them requires that my structure will have at least n elements. And I have this phi n for all n. So I have the requirement that my structure will be infinite. Okay? And notice that we've done all of this with just the empty language. Now what happens when we try to look at more interesting languages? I mean, I can define much more stuff. So let us look at the next step, let's look at a little bit richer language. So now This was all examples with the empty language. Now let L be a language in which I have a single two-place relation. Now I can define lots of stuff. So let us see what we can do. Lots of stuff. For example, how do I say the set of all structures in which I want to say that the set of all M such that the interpretation of R in M is an total order. Total order, I mean, it orders all of the elements of the structure, and it's an ordering. So now we get into really feeling how first-order logic can really express everything that mathematics does. So what I have to say in order to make sure that this interpretation is an ordering? What are the requirements of this relation that will make sure it's an ordering? Yes?
For every pair of x, y, either r, x, y, or y.
Right.
R, y, x.
So I'll have here in my sigma order, I will have things like, I'll have first that for every pair, for every x, for every y, r, x, y, or r, y, x. That's one requirement. What else do I need to put in my set to make sure it's an ordering? Yes?
Has to be commutative, so for all.
Commutative, what do you mean?
So, well, not- for
It's
all-
transitive.
Transitive, like for all x, y, z.
For all x, for all y, for all z,
All of x, y
r of x, y,
imply.
and r of y, z implies r of x, z. Right? That's transitivity, the transitivity of ordering. Now note that this doesn't suffice yet. I can cheat. How can I cheat? Can you give me a structure in which R is not an ordering, but it satisfies these requirements? Yes?
Can have like a cycle?
Not just a cycle. I can say every two elements Rxy holds. I can say Rxy holds for all pairs, for all the pairs. So it will satisfy this for every pair, this or this, and it will satisfy this, because Rxy will hold for every x and every y. So what is missing here to make sure we're not cheating? That it's really an ordering and not just throwing everything into the bag? Yes?
For all x, for all y, all of xy implies not all of yx.
Right, so now it depends whether we want it to be a strong ordering or a weak ordering.
Yes.
So this will be a strong ordering. What did you want to suggest?
I want to say for all x, for all y, rx, y, and ryx imply arrow x equals y.
Right, that is exactly what weak ordering will give us. For all x, for all y, rx, y, and ry, x implies x equals y. Remember that we do have equality in our language. So those three requirements define the set of all total orderings. What do you mean by total ordering? That every two elements are comparable. And we can talk about other elements. For example, how do I say that my ordering has a first element? If I want to distinguish the natural numbers from the integers, so the difference is that it has a first element. So how do I say a formula that gives me the set of Sigma is order with first element, minimal element. How shall we say it? What requirement should I add? Yes?
There exists an x for all y such that
Right.
r is y.
There exists an x such that for all y are xy. And how do I say there is no maximal element? Yes?
For all x, there exists a y such that r xy.
And they are different. Because otherwise it will be the same guy. Right. So I'll say for all x, there exists a y such that r xy and not x equals y. So now I said there is no last element. And there are many more interesting properties. How, for example, how can I distinguish the integers from the rational numbers? The order of the integers from the order of the rational numbers. Do we have a formula? So in other words, what I'm asking is, let M1 be the integers. Integers is positive and negative integers, with R of M being less or equal in this structure. And let M2 be the rational numbers with the same ordering. Now I want a formula that will hold in M2 and will not, a sentence that will hold in M2 and will not hold in M1. A sentence that will distinguish between them, yes?
For all x, for all y, x equals y, or there exists z such that r
Right.
of x, z, and
Right.
r
So,
of
right.
z, y.
So this formula is called that the ordering is dense. Between every 2 points, I have a third point. This is called density. So I have this phi of density. The ordering is dense. And phi of density says for every x, for every y, if it's not the case that x equals y, then there exists z such that r x. Oh, I have to say what the ordering between them, right? So say, okay, so not xy and, let me just fix it here, not xy and rxy, then there exists z such that not x equals z and not y equals z and r x z and r z y. Right? So what I'm saying is for every x and y, there exists some z living in between, which is neither of the two. And can I, in this language, distinguish between this structure and M3, which here I will take the real numbers, and the ordering on the real numbers? You see what I'm trying to do now? I'm trying to say, is there any property of the ordering that distinguishes the rational from the reals. It turns out that there is such a property, but we cannot express it in first-order logic. I mean, just for those of you, I mean, how many of you know what is the difference between the ordering of the rationals to the ordering of the reals? Have you heard about Dedekind cuts? It is the property that whenever you have an initial segment, there is a least upper bound to the initial segment. If I take a collection of points that is closed, downwards closed, that is, if a point is here, everything below it is here. Then, and it's not everything, then there is a least element that is outside or a maximal element inside. It is called a Dedekind cut. It's a cut in the ordering, and the cut has a minimal element outside it or a maximal element inside. And the real numbers have this property. The rational numbers don't have this property. For example, if I look at the set of all rationals number R such that R squared is less than 2, then I will get such a cut without a top, because the top element should have been square root of 2. And square root of 2 doesn't exist in the rational numbers. It's not rational. Anyway, we don't want to get into other types of maths, but we can see that this is a very rich language, the first-order language. It already allows us to express lots of stuff just with one relation. But with one relation, I can also express stuff which is not about orderings. I can express something completely different. For example, how can I say that R is an equivalence relation? Do you all know what is an equivalence relation? An equivalence relation means that it takes the universe and partitions it. It takes the universe. Here is my universe of the structure. And it partitions it into sets such that every two elements in the same set satisfy the relation between them. And every elements which are in different sets don't satisfy the relation. So I want to say that R induces a partition of the universe. Partition such that every two elements in one part satisfy the relation, and every two elements in different parts don't. That's called an equivalence relation. So what will be the sigma for equivalence relation? Sigma for equivalence. We'll say R is an equivalence relation. So we'll have here an axiom that say equivalence relations are transitive, symmetric, and reflexive. So transitive means what we have here. For every x, for every y, for every z, r, x, y, and r, y, z arrows r, x, z, the same formula that we saw here. Symmetry means for every x, for every y, r, x, y implies r, y, x, which we didn't have here. And reflexivity will say for every x, r, x, x. So this defines the set of all equivalence relations. But the R can be interpreted not necessarily as, you see, so here we talk about orderings. Here we talk about arbitrary sets. But we can do all kind of more very, very different stuff. I can talk about graphs. So I can talk about the set, all the universe in which R is a graph. You remember, if I have a collection of points, if I have a graph which is a collection of vertices and a collection of edges. I can describe it as a structure for this language, that whenever I have an edge, those two satisfy R. So every graph can be viewed as a structure for this language. So given any graph G, which is vertices and edges, it may be viewed as a structure for the language that has just R in it, two-place relation. How? What is going to be MG? What is going to be my universe? What is going to be my universe? If I want to interpret this as a structure, what will be my universe? The vertices. And what will be R of M? The set of edges. So R of M will be just the set, so I'm just repeating it. So R of M will be just the set of all edges. We said R in a structure is a set of pairs, if R is a two-place relation. So it will be the set of all edges. So now suddenly I can, in this language, express properties of graphs. So can I, for example, how do I say the set sigma that tells me the graph is a clique? You remember what is a clique? Graph which is a clique? It is a graph in which every two vertices are connected by an edge. So how will I say that my graph is a clique?
For all x, for all y, r, y.
Right. I'll just say for all x, for all y, rxy. So now I can talk about properties of my graphs. Or I can talk about the property of a graph being connected, or a graph being all kinds of properties of the graph. So what I'm saying is that we have a very kind of rich language that can express many things. One, or maybe my last example of what we can express with the language before we move on with definitions and theorems is that the example of talking about a universe of sets. So if you want to define a universe of sets, I can say for this same language that has only one two-place relation R, I want to talk about an interpretation as sets. So I want to talk about the following, that my universe M is going to be a collection of sets, and R of M is going to be the epsilon relation, member of. So now I can describe what is a collection of sets. So how can I say, for example, there exists an empty set? How will I write a sentence that will say there exists an empty set in my collection? Yes? For all x, there exists y. So you will tell me for every element there is someone inside. I want to say there exists an empty language, an empty set. There exists a set with nothing inside. What?
Yeah, well, there exists x such that for all y.
There exists x such that for all y, not rxy. such an X will be an empty set. Nobody is a member, no RYX, not RYX. Or how can I say there exists a universal set? The biggest set, all other sets are members of it. How will I say that? What?
The same formula, remove not.
So there exists a set such that for, remove the Y, right, remove the not.
Oh wait,
Right.
that formula, doesn't it also have to include, wait, never mind.
There exists an X that nobody is a member of X. Notice that I'm talking about member of and not subset of.
Okay, but so wouldn't the universe have to include both elements and sets? Oh, I guess sets can contain sets.
Yes.
Right, so when talking about sets, so some of them could be subsets of others. Right, I can talk about a set that looks like the set A and the set AB. So this set, I can call it C, and then I can say, yeah, and everything could be sets. But that's set theory, and we will not get into this, because that is going to be very confusing. Okay, so what I wanted to say is that we have here a very rich way of expressing, even with very narrow languages. And actually, when we do mathematics, I don't know how many of you took courses in algebra about group theory, you don't know, vector spaces, fields. Everything is expressible in the language. So if I want to talk about, for example, of the set to define fields, I want a sigma that defines all structures that are fields. So remember, a field is a structure in which we have addition and multiplication, and we have a zero element, and we have a unit element. And we have all kinds of rules. So I will need a little bit richer language. I will need a language that has I will need a language that will have two functions, f, a two-place function f, a two-place function g, and I will need a constant a, and I will need a constant b. So until now, we talked about languages that just contained relations. Now I'm talking about a language where these are function symbols. And these are constants. And now I can say I want to describe fields. So I want to say f is the addition. So I want to say addition is commutative and associative, and A is the zero element, and B is the one element. So I can say things like, for every x, for every y, fx y equals fyx. So what did I say here? In terms of addition, what did I say about my addition? If f is the addition is commutative. X plus y equals y plus x. And I can say, how do I say that A is the zero element in my field? How will I say that A is the zero element, plays the role of a zero? Yes?
G is the multiplication one, right? So you can say for all x, G, A equals A.
Right, or I can do it with addition also. I can say for all x, fxa equals x. Or I can say for all x, g, x a equals a. And what is the formula for all x g x b equals x? What does it say about b? B is 1. So last toying with this example, can you give me the distributive rule? How will I write that x times y plus z equals xy plus xz? How will I write this, the distributive rule? Yes.
For all x, for all y, for all z.
Right. For all x, for all y, for all z. And then I want to say, right, so let's be careful. We want to say g, I want to multiply g of x and f, y, z equals f of gxy gxz. Right? You see now I'm treating now function symbols, so it's different than relations. Because now all my formulas are not, and a relation Rxy is an atomic formula. When I talk about functions, f of yz is just a term. It's not something that can be true or false. What can be true or false is equality. So it's really the case. I mean, I hope that you can start getting the feeling that we can express everything that we do in mathematics in first-order logic. And in first-order logic of a very limited language. We need maybe one relation symbol for ordering. We need two function symbols for plus and times. Maybe one or two constants. And now you can talk about any domain in mathematics that you want, and the language will express graphs, sets, orderings, groups, fields, vector spaces, everything we do in math. So this is a very useful language.
Did you just say we couldn't express Dedekind cuts?
Yeah, there are things that we cannot express, and
That's part of mathematics.
that's part of mathematics. But we can, what I mean by that is that we can define all the objects that we are talking about, I mean, fields, groups, the universe of sets, we can define with this language, right? But we will see the limitations. That will be very interesting to see what are the limitations of first-order logic. And for that, that's why it's called first-order logic. We also have a second-order logic. And we don't have a third-order language just because things become so complicated that the mathematics that we usually invent doesn't go that far. So we do have second-order logic just for the things we cannot express here. Okay. So we have this notion of defining a set of structures. A set of structures is definable, and depending on the language, we can define the set of all groups, the set of all fields, the set of all orderings, and so on. Now I want to talk about another notion of definability. So another notion of definability is the notion of definability within a given structure. So what do I mean by that? I have a structure and I want to define a subset of its element. So let us look at, let me start with an example. So my example will be, I'll take as an example, let my language be the similar language to what we just had. So I'll have my language with f, two-place function f, two-place function g, even a one-place function s, and a and b, and no relation. So those are function symbols, and those are constants. We always have to state explicitly whether it's a function symbol or a relation symbol, because the notation is the same. And let my universe M be the natural numbers with F interpreted as plus, G interpreted as times, S interpreted as the function successor, x goes to x plus 1, so that's S, the successor. A is 0 and B is 1. So I gave you a structure for this language because I told you what the universe is, and I told you what is the interpretation of each of the symbols. So now we have a fixed structure. We don't talk about defining a family of structures. We fix the structure. Now that we fix the structure, I can ask, can I write now a formula such that it will hold only for the even numbers? So this is definability within a structure. So I'll say a formula phi of x with a free variable x defines a subset A of the universe of my given structure if M satisfies under an assignment S phi of x if and only if S of x belongs to O. I used S here. Oh, belongs to A. So let's replace the successor with a different. So how can we call successor? What?
Add 1.
Add 1. So I for increment. Okay. I for increment. Next will be the natural numbers, right. Okay, so now I want to say I have a notion of defining within a structure. I want a formula that holds only when S puts here someone from A, and fails when S puts here someone which is not in A. So can you give me now a formula that defines the subset of all even numbers? So what would be phi even? It defines all even numbers. Phi even of x. I want to write a formula that will hold in this structure if and only if under S assigns to x an even number. Yes?
There exists a y such that f y is a
Right, right. So I can write there exists a y such that f y equals x. There exists an element such that if I add it to itself, I'll get x. It tells me x is, this will hold. You see, this is a formula whose only free variable is x. The y is not free because there is a quantifier on y. So it's a formula in only free variable x. And it will hold for a given assignment s if and only if s assigns to x an even number. And of course, we can write odd numbers, which will just be the negation of this. So this is definability inside the structure. Let me give you a more difficult challenge. Can you give me f prime and tell me x is a prime number, phi prime of x, that will define the set of all prime numbers in this structure? Yes?
For all y, for all y is not equal to 1 or a.
Okay. So yeah, I mean, I'm on the way, and you don't have to. I mean, it takes a little bit of time to organize your thoughts.
Yeah.
But so take your time. How shall we say it? Yes.
For all y, if there exists a z such that g z y is equal to x, it implies that y equals 1 or y must be
Right.
or y equals x.
Right. So we can say for all y, for all z, if g, y, z equals x, then say y equals x or g or z equals x, right? If I multiply two numbers and get x, then one of them should be x itself. One is not considered a prime?
Yeah, one is not prime.
Okay, so we can say and all of this and not x equals b, because b was my 1. So x is not 1, and whenever two numbers multiply to x, one of them should be x. So I can define a set of all primes. And I can also define sets of tuples. So for example, how should I define the ordering relation in this language? So I want to define the set of all pairs such that x is less than y. So I want the formula phi less than xy. So now I will have two free variables in my formula, and it will hold if and only if s assigns to x a number which is less than the number it assigns to y. Any fresh participant? How will I say in this language s is less, x is assigned a number which is less than the one I assigned to y? Yes?
There exists some z such that f x
Right.
z is y and z is not equal.
There exists some z, if I want less than and not less equal than, there exists some z such that f x z equals y, and it's not the case that z equals b, z equals a. A was my 0. So I can express addition in terms of the ordering. And then you can ask all kinds of interesting questions. Like, for example, if my universe was the set not of natural numbers, but same interpretation for f, g, a, and b, but now my universe is the set of real numbers. So now I have a structure M prime, which is the real numbers, with the same interpretation, with plus times x goes to x plus 1, 0 and 1. Now I have the set of real numbers. Can you, for example, define a formula that will say that the number is non-negative? Do you have phi of non-negative x? I want to say x is not a negative number. X is positive or 0. Yes?
There exists y such that g, y, y.
Right. I will just say there exists y such that g, y, y equals x. It means x has a square root. We know that the only real numbers that have square root are the numbers which are non-negative. Right? So lots of things are definable. Is every subset definable? Say I take here the set of natural numbers, and I ask, is every subset of natural numbers definable? And now we should just have counting arguments. I mean, for those of you that attended the special lecture that we did a couple of weeks ago. The point is that the number of all formulas that we can write in this language is only countable. It's infinity, but it's small infinity. But the number of subsets of the natural numbers is infinity, but it's a big infinity. So I don't have enough definitions for all the subsets of the natural numbers. There are more subsets than definitions, which is similar to the situation that we saw in propositional logic. Remember, in propositional logic, we said we cannot define all subsets of truth assignments because there are too many of them. There are sets of truth assignments that I cannot define. Here it will be the same. There are subsets of natural numbers which are not definable. Just because there are so many subsets, it's a big infinity, and the number of formulas is small infinity. Now, how can we point to a specific non-definable set? How did we point to a specific non-definable set of truth assignments in propositional logic? What tool did we use? Do you remember? Probably it's my fault that I didn't put it in the midterm, so nobody remembers. We had a tool for showing that things are not definable. And that was the compactness theorem. Remember, we saw that the compactness theorem, and we will have the same here. So the next step, okay. So let us just recap on where we are and tell you what the next step is, and that will end our lecture today. So we said that no matter which logic we talk about, we are going to follow the same path. So we have syntax, we have semantics. We start the discussion by defining the set of all well-formed formulas. We did the same in propositional logic and in first-order logic. Then we have defining the semantics. In propositional logic, it was the truth tables. In first-order logic, it was defining the notion of a structure, and when is a formula structure and assignment, and when is a formula satisfied in a structure. Then we started talking about all kinds of semantic notions. So we had here a tautology in propositional logic. Here we had a logical truth, logical implication, and we also talked about definability. Definable, but definable here had two versions. Set of structures and subsets of fixed universe. So in propositional logic, we only had definable in terms of sets of truth assignments. But here we have two versions of definability. Then the next step, what we did was we talked about the compactness theorem and showed that the compactness can be used to show that some sets are not definable. And then we went back to the syntax, and what was the next step in the syntax? We defined the proof system, right? And then we went and showed connections between what we can prove and what is logical implication and consistency and satisfiability and so on. So we're going to follow the same path. Our next step is going to be compactness and showing how it shows undefinability. And then we're going to go into a formal proof system. So we're following the same track, but richer and more interesting logic. Thank you. Have a nice weekend.